Good. Camera webcam कहाँ है याद है? Any idea where the webcam is?
ऑडियो चल रहा है।
Hello guys. So event is going to take 10 more minutes to start. Please bear with us.
डेमोस का वो फाइनल है ना, सिर्फ इधर ही
Perfect. हाँ?
डेमोस इधर ही होंगे सिर्फ।
नहीं, डेमो के टाइम पे अपीयर के थ्रू हो जाएगा। बोलो।
अगर यहाँ पर कुछ सवाल पूछे तो आपको सवाल भी रिपीट करना पड़ेगा। क्यों तरह? वीडियो ड्राइव पे up.AI वाले ड्राइव वीडियो इस समय try not to ज़्यादा entertainment करना है। अरे पासवर्ड अबे एस्केप करना है।
वीडियो भी अच्छा आ रहा है। एवरीथिंग रेडी। वीडियो
हाँ तो वॉल्यूम में
yeah, videos. Yeah,
डाउनलोड कर लो वो लिंक।
Hello, we just need 5 more minutes and we will start. We're just setting up the next Five more minutes, we're setting up the live stream. Sorry for that.
हो गया ना? चलो go. Just किसको टीम फिल करूं? निखिल ने
हम ट्रेनिंग में स्टार्ट करने के लिए फाइनल राइट नाइस
This yes. Whenever is that? So if you stop, want the mic to stop, just press this button. Okay. And now it's off. Press this, it will on. Right. Play it. Play it.
आयान किधर स्क्रीन अपनी सेट करो एक बार अपनी सेट करो तो के लिए ऐसे किया सेट
Everything's ready. Awesome. Let's just invite everybody and then start. Audio and please start. अलग से करना पड़ता है और वो नहीं है आपको
पर्सनल इनवाइट भी भेजा तूने नहीं आई डोंट थिंक सो आई डोंट थिंक सो
Let's begin. Hello guys, welcome to up.AI Summit 2018. This is the first of its kind event in IIT KGP. Okay, this is hopefully going to be IIT KGP's flagship artificial intelligence event, which is going to happen every year. So we have tried very hard to put together an event this year. So let's see if we can continue every year. It depends upon the kind of response that we receive from you guys this year. Okay. So it's going to be 2.5 days of extremely happening times when we are going to have guest lectures. Tonight we are going to have hands-on tutorials so that you know exactly what is AI and you get up to speed with what is the latest and greatest, and also you know what it takes to achieve what, because it needs a lot of context to actually listen to the experts and who are going to come up with the next 2 days. So, I think you already know that 8 out of 10 jobs today actually need some bit of machine learning or artificial intelligence profile, right? And that actually means that the demand is only going to increase over the next few years. Yeah. Hello. Can you hear me in the other room? Perfect. Okay, great. So yeah, it's a bit awkward, but yeah, we have to have. So it's so encouraging to see that there are so many people who are interested in artificial intelligence, because we actually had to do 2 parallel sessions. So the video and the audio here is getting live streamed in the other rooms, and hopefully everybody will be still checking.
just go
Okay, you handle this. Okay, yeah, let me keep talking. So, just see so many people interested. Yeah, so let's do a quick poll. How many first years here? Wow, that's so amazing. Somebody take a picture. So many first years here. Awesome. So, so you know that you're going to graduate in 4 to 5 years from now, and at that point of time, you won't be just competing with other humans, but also you're going to compete with other machines because more and more jobs are getting automated every day using artificial intelligence, right? So today, the kind of code that we write, most of the tasks can actually be done by AI. So AI can actually run that beautiful, extremely structured and professional code. So even a lot of coding jobs are also at stake. So when you'll be graduating, you have to get that rare set of skills that cannot be repeated by AI. So it's actually very interesting times to live. Okay, again, a quick poll. By the way, a lot of goodies are actually coming in, so we are going to we'll keep having this kind of questionnaire and this kind of quizzes, and we will be giving out goodies. So yeah, stay tuned. Okay, I'll have my headphone. Yes. Perfect. Okay. I know I'm looking awkward, but anyways. Okay. Cool. Perfect. So we would like to. So tonight's evening, I'm saying. Okay. Today evening has been planned in this way. So we are going to pump you up totally. Okay. With all the latest and greatest, and try to get you excited as much as possible, and also give you the necessary bits of information, and so that you can actually go back and study harder. And if you want a career in artificial intelligence, we'll be sharing a entire list of resources, which I recommend that you actually use your phone cameras and take pictures of, because that's going to be a lot of help when you would actually focus on planning your next steps in artificial intelligence, deep learning, machine learning, whatever, right? So, okay, let me do another poll. How many of you have heard this term for deep learning? Wow, most of the first years have heard deep learning already. Okay, let me ask another question. So, how many of you heard this term after coming to the campus? So, you already knew about deep learning when you were in your schools. Amazing, that's amazing. So, this is very relieving to see that in India, our schools and our media are actually covering a lot of development that is happening in deep learning and artificial intelligence sphere. And this actually shows that people in our country are at par with the best institutes in the world. Really, I mean, at least when you look at the landscape of AI, so clearly China and Canada and US, they are just killing it, but we are not very backward. So maybe I can expect that 5 years down the line, we would be publishing at the same volume, we would be developing the same volume of technology which is being done by China or Russia or US. Perfect. So we are going to begin the session with a video, and after that we will be taking you through a journey through history, and then we would be going into the theoretical and practical details, and all the demos are going to happen at that time. And after that, we are going to tell you how you can get started on your own laptops. How can you install all the necessary libraries and everything? How to choose a problem, and how to run the code in the best possible way, right? So that you can get as much performance as is actually demanded by the application that you are trying to solve. Okay, so having said this, we will play this video for you. Unfortunately, there is no audio output, but I'll try to show you as much as possible. So what you are seeing is, what you are watching is NVIDIA self-driving car actually. So this car can literally drive itself, and it's actually driving along a road which is extremely historic because a lot of transportation, a lot of important events in the history of transportation have actually happened on this particular train. So NVIDIA is one of the leading developers of hardware, so you just know them by the graphics cards that they make. Even that, those graphics cards just happen to be a very good choice of hardware for machine learning, and they actually fueled the deep learning revolution to a huge extent. So you can see that they can. This is a standard United States highway, and they can like easily switch. So this, I think many of you have heard already. So this is Google Duplex. So Google has actually made a conversational agent which can make a phone call on your behalf and make an appointment. And it's practically almost like it's impossible to distinguish whether it's a human speaking or it's a machine speaking. So it actually, like, has those little bit quirks and deficiencies that humans have when they are talking, right? Like at one part of time it just says that, see, so now it's the machine that speaks. So you saw that it actually did a and it's when you hear this kind of a gesture, then it's pretty much you think like you're talking to a human being, but it actually uses this as a filler while it's processing. Okay, so this like not only the AI can actually AI of today can not only imitate human beings at the work that they do best, but also they can even model the deficiencies that human beings have, the mistakes that human beings make while they're working, and this is like pretty much indistinguishable from human beings, and it will just get better and better every year. So you can see a full conversation that's happening over here. Yeah, so over here, what you're going to see is that this is not driven by any kind of machine learning or deep learning. So this is traditional control theory, but this actually is the kind of AI which gets deployed in the real-life applications where you have safety and criticality associated with it. We have to give performance guarantees. See, it's as dexterous as a human being, and this is a real demo. So you can see the kind of coordination that's happening between the different parts of this robot. So this is called the Atlas robot. It just did a backflip. So this was considered as one of the toughest feats in robotics. It was very hard to do before. So this is, let's check this out. So this is Bixby. This is Samsung's virtual assistant. I think you already know about it. It comes with Samsung phones. So this can control all of the smart appliances in your home. It can control your phone. It can control your TV. You can just talk to it, just like you do it to, just like you talk to anybody else. It even wishes you good night. Okay. Having said this, so these are a couple of examples of use of AI in our day-to-day life. So AI is no longer science fiction; it's a reality. Okay, it's actually happening every day. You're using it in our lives and penetrating with every single Google I/O, with every single Microsoft build, and every single Apple WWDC. Okay, and Facebook F8. All of these developer conferences, by the way. So if you have not started watching these events live every year, you should be doing, because these are the companies that are pushing the revolution in artificial intelligence. So what I say is our Google I/O stands for input output. So that is Google's annual developer conference. Microsoft's is called Build. Apple's is called WWDC, Worldwide Developer Conference. And Facebook's is called F8. Okay, so you should be watching all of these conferences live, which we all watch. So yeah, so first session is called Getting High on AI. I'm going to take you through a journey in artificial intelligence, like how it actually evolved over the years, right from the prehistoric age. And I forgot to introduce myself. So yeah, I am a very senior student here in IIT KGP. I joined in 2011 in Civil Engineering Department. My name is Anirban Kantara. So over there, I did my first year, then I did a FC. I came to electronics department, and I used to work in semiconductor devices. So I actually published a paper in my second year, and then I fell in love with machine learning. So I started working with Professor Dev's sheet, and one of the students is going to present here as well. It's absolutely amazing. He has some really great projects going on. So at that time, he was a PhD student. I kind of followed his steps till today. So after that, I started working in machine learning very deeply, and also I'm one of the first researchers in IIT KGP to work on deep learning. And then I joined PhD directly after completing BTech. I didn't go abroad. I thought that we can stay back in India and make a difference. So currently, I'm doing my PhD in the Department of Computer Science and Engineering. I'm a Google PhD fellow, so Google sponsors my entire PhD. And I'm also an Intel student ambassador for AI. So you see this t-shirt, so I am representing Intel AI tonight. So I'm going to talk about all of those programs, and like it's really interesting. And I just entered my 4th year of PhD, and things are going pretty well actually. So yeah, so I'm going to kick off your journey in AI for the people who are just beginners. So yeah, let's all get high on AI. So what is AI? What is artificial intelligence? So artificial intelligence is mankind's quest to make a machine which can actually replicate its thought, which can actually think like itself, like a human being. So man always wanted to make a machine because which can actually augment its thinking, its cognitive abilities, because that's what actually needs another human being. So if you can have a machine do that, then you can actually increase your productivity. So this was the idea. This was the this was the motivation right from the beginning, and it is totally built upon this assumption. It's totally built upon this assumption that human thought can be mechanized. So this is actually very deep. So human thought is something that is actually considered very sacred and very unique. But can it be mechanized? Can a mechanical instrument, can a machine actually replicate and think like a human being? Yeah, so it actually started in the ancient age. So ancient Chinese, Indian, and Greek philosophers actually envisaged the existence of machines which, like artificial humans, right? And they had a lot of theory and a lot of stories. So right from like the first millennium BC to 1500 AD, like philosophers like Aristotle, Euclid, and William of Ockham, they introduced this entire field of philosophy, then called philosophy, now called mathematics, called formal reasoning. So formal reasoning is actually a good name for mechanized reasoning. So human reasoning, the kind of reasoning we do as humans, that is human reasoning, they wanted to find a way to do formal reasoning, which means they wanted to mechanize the reasoning. How to get a machine to think like a human being. So they had their first bits and pieces of theory at that particular point of time. Then between early 16th century and up to 19th century, there were this entire extremely rich field of symbolic logic developed. So you are actually going to have elective classes on elective course on symbolic logic. So I would like to say that is the one of the precursors of AI. That is where all the concepts actually came into being, right? And Leibniz, Hobbes, and Descartes were actually extremely famous philosophers who pioneered in this area. And then, right from early 20th century, these concepts started becoming more and more formal and more well-defined. So symbolic logic actually introduced the concept of representing thoughts and entities by symbols and then connecting them with reasons. So mathematical logic, this particular field, actually brought all the different kinds of relations. They brought the symbols together, and then they devised this language called Boolean algebra, right? So many of you all know about OR and NOT and all of these operations, right? So these are logic. This is actually a language with which we can represent any algorithm, any problem, any workflow can be represented mathematically in form of these, in this particular language. So this was the beginning of all of the endeavor that has been going on over the ages. So all they wanted to do is try to represent human thought, the way humans solve problems step by step, right? In the form of an algorithm. To represent that in a mathematical form that can be solved by a machine. So this is when the mathematical, the fundamentals of the mathematics, underlying mathematics, was created. And then I'll take you through some milestone events in this entire process. So in 1642, Pascal invented the mechanical calculator. It was the first of its kind in the world, and it was just make sure that the calculations that are happening in those early industries, right, in these early offices, don't go wrong. They are like the same every time, right? to remove the human error from the loop. And that actually remains the same. The motivation actually remains the same till date for AI. The reason we want autonomous cars, right, is just because we want to remove human error from the loop. It has been seen that if you can remove the human being from the steering wheel, from the driver's seat, then you can actually cut down the rate of accidents by up to 89%. Okay, so at that point of time, people were not thinking about driving cars because it was 1600. Okay, barely there was any kind of motorized car out there. So they were thinking that, okay, I don't want my calculations to go wrong in my business. That's why they made the mechanical calculator. Then came Alan Turing in 1936. So fast forward to 1936, so many years, right? He actually, so a lot of this like mathematical logic, symbolic logic, all of these theories have been developed in there. So Alan Turing, as you may know from the movie called Imitation Game, how many people watched the Imitation Game? Wow, again, most first years have already watched Imitation Game. Great. You people are advanced. Evolution is real. So there you must have seen, right, that how the idea of computer came into being. They wanted to crack the German Enigma code. And Alan Turing made a machine which could actually work very, very fast, much faster than a human being, and actually crack the code within a period of 24 hours. So that was the first artificial intelligence that you can say come into being, like in the true form. So Alan Turing is sometimes called the father of artificial intelligence. So he actually made it possible to actually think like a human being, do all of this number crunching within a very short period of time. And that's when the concept of computer also came into being. So after that, in 1939, the Church-Turing hypothesis said that this is extremely historic. Okay, so try to like follow it line word by word and see how these people, like the depth of work that these people did. So they said that any function of natural numbers, okay, is computable by a human being following an algorithm. So they are challenging the human being. They're saying that, okay, if a human being can solve a particular problem of natural numbers, any function of natural numbers, following an algorithm, ignoring resource limitations, if and only if it can be computed by a Turing machine. So human capabilities can be actually bounded by the Turing machine. So this means that anything that a man can do can be done by this machine, which Turing made. So that was the first real, extremely capable artificial intelligence that was created back then. Okay, so after that, the Turing test came into being. So the idea was like people were asking questions on how to know that we have made a very effective artificial intelligence. So they devised something called the Turing test, in which they say that, okay, suppose you go to this booth where you sit down and so and then there are the two voices that come to you and you make a conversation. So you cannot see whose voice it is. You can just hear the voice, or you just get like written transcripts, like written conversations, like a text message. Okay, text conversation on WhatsApp. So there'll be two entities talking to you over text message, and if you can understand which one is a machine and which one is a human being, okay, then the machine has failed. So the machine is going to try to convince that you are talking to a human being. Okay, just like Google Duplex was trying to do. Okay, so that particular point of time where you would not be able to distinguish between the human and the machine, who just spoke to you, you will say that the Turing test has been passed by the AI, and it's like a true AI. So that's like a really capable AI. So that was the Turing test. Is everything all right? Yeah, so now come to 1957, this guy called Frank Rosenblatt invented something called perceptron. So how many people have heard about perceptron before? Ah, awesome. Okay, rest of the people note the name. It's called perceptron. Okay, that is where all the deep learning story starts from. Okay, so they say that so he studied the way neurons are organized in the brain, and they tried to find a mathematical model of the neuron, and saw that it can be as simple a computational neuron. So each neuron is actually very simple. Each neuron is actually very simple. So it just adds up all of its input and makes a non-linear transformation. That's it. And it's a simple piece of computation. But the good power is that if you can assemble a lot of those neurons, it can model some really complicated functions. So any kind of problem solving, okay. So maybe by now you already understand the concept of a function. A function just takes a bunch of input and produces an output, right? So any problem in the world can be posed as a function. Okay. For example, if you are driving a car, then the function is there should be some function which should output the amount of steering wheel, the amount of accelerator that you need to press at any given point of time, given the inputs that you can see, given your visual inputs. So the task of AI is to actually, the task of machine learning rather, is to actually model this function, which maps the inputs to the outputs. So this was the beginning. So he proposed that this particular mathematical model of a perceptron, sorry, yeah, can actually work as an extremely powerful function approximator, and then they made this machine that you can see on the right, on the left, that consists of a huge number, about like a lot of those small units, perceptrons, which they created as a hardware unit, and all the weights were these tunable resistors, right? And so after every iteration of training, you would be tuning those resistors and training the neural network. And all of them would look at a 400 pixel image and try to recognize what particular image it is. So that was this machine. So that was how all the neural networks began. And then what you can see in this, so in 1989, so it was not very far back, right? So it was like just in a period of about 30 years, there is this car, so which is a retired army ambulance, which is driving on its own. So this was the world's first self-driving car, okay? And it used this single hidden layer neural network, the single layer neural network, not even a hidden layer. Sorry, yeah, with just 5 hidden units, which would look at the scene from the camera and would predict the steering angles. So it was an amazing feat. So it happened in CNU. So this particular guy, Pomerlau, was like, this is like absolutely the forefather of all kinds of autonomous driving technology that you can see. It's an amazing feat that happened in 1989. It was the world's first self-driving car. And then in 1997, everybody knows about this news, right? So IBM Deep Blue, so that's a very sophisticated, like extremely highly handcrafted artificial intelligence that could beat Gary Kasparov. So that is considered as a huge milestone. And then in 2006, right? So what happened to neural networks after Pomerlau? So at that point of time, so Rosenblatt and like the people who followed it, right? They had actually proven that a neural network with more than one hidden layer, so we will come to all of those terminology later on in this talk, that if you have enough nodes, then you can model any function in the world, any problem in the world can be solved by a neural network. This was given. This is already proved. It was called the neural network as a universal function approximator. But back then, the computers were so slow and so weak that any serious application, like any relatively complex application, would not be able to. It was not possible to model using a neural network. The neural networks, optimizing the neural network was extremely hard, and the algorithms were also not good. So a lot of developers. So people actually lost interest of neural networks. Okay, and people were doing other kinds of machine learning algorithms like support vector machines, decision trees, and others, which were easier to tune and easier to train. But in 2006, something really interesting happened. So this guy Hinton, so his full name is Geoffrey Hinton. So he is now called the godfather of deep learning. He invented this algorithm called backpropagation back in 1989. Okay, so that particular algorithm is used to train all kinds of deep learning algorithms today. So, but nobody cared about that algorithm until 2006, when he and his student, his name is Ruslan Salahudinov. He is now the head of machine learning at Apple, and they introduced this new algorithm called unsupervised layer-based speed training. And using that, they could actually train a very deep neural network. So the question was that, okay, neural networks with a couple of hidden layers would not be able to model serious functions. But what if we can make a lot of hidden layers? Like we can actually make the neural network a lot deeper. We actually have a lot of trainable parameters, so that is possible. So that is like a very flexible ball of rubber, which you can like actually tie and distort into any function, any shape that you want. Okay, so that's the entire idea between deep neural networks. The deeper the neural network is, more the number of hidden layers that you add, right? So each is a layer. So each box is a layer of neurons. So more the number of neurons you add, the more is the amount of non-linearity that the neural network is able to model. But the question is, can you optimize it? Can you actually fit the function? So he actually introduced this amazing algorithm called unsupervised layer-based training. And using that, he trained a kind of neural networks called deep autoencoders, and that actually kicked off the interest in deep learning. Yeah, and then in 2009, this amazing lady, her name is Fei Li. She is from Stanford. So during her PhD days, she actually created this data set called ImageNet. And this particular data set has 14.2 million images of 22,000 categories. So every year, a huge challenge happens. So it is called the ILSVRC. So it's called the International Large-Scale Visual Recognition Challenge. So in that challenge, you have to actually be able to identify all of these 22,000 categories of images. And that actually fueled the deep learning revolution because all the big players came in and they competed against each other to make better and better neural networks that could actually solve this data set. Yeah, and so during 2012 and 2015, fueled by two things, okay? So number one was image and data set. Number two is the easy availability of compute. So NVIDIA made a neural network library. It's called the CUDNN. Okay, and another framework came out of Berkeley. It's called Caffe, and everybody was using that. And NVIDIA's GPUs were available for very cheap, and they were working extremely well for deep learning. And so a huge amount of data was available. Algorithms got better every day, as well as free and cheap compute was available. So people were like, so a lot of development happened between 2012 and 2015, and it's called the deep learning revolution. So you can see from the right is like old, to the left is new. So there was a sharp like improvement of about 10%, right, between 2011 and 2012, and that's due to a deep neural network called AlexNet. It was made by Alex Krivsky and Geoffrey Hinton out of Toronto, and it actually just shocked the world. Everybody thought that deep neural networks are of no use because nobody cared about them for all of this time. But suddenly they came in and created a revolution. They beat the previous state of the art by a huge 10%. And 10% defeat is like a huge deal. It hardly happened again. So then year over year, the layers got deeper and neural networks got deeper, and it finally achieved this level called this accuracy of 3.557%. So this is actually better than a human being, right? A trained human being has an error rate of around 5%. So it could actually beat the human beings at 3.7%. So that 3.57%, and at that point of time, it was declared that okay, fine, visual recognition has been solved by AI. So that's actually a huge. That's the reason why everybody is interested about deep learning. And you in your first year, you have already heard about deep learning because a huge revolution has happened. Now machines can actually recognize objects better than human beings. So that's a huge deal. So then in 2016. There is this agent called AlphaGo that was made by this company called DeepMind, which is a subsidiary of Google right now. It beat the world's one of the legendary, like the founder of this game called Go, which is an ancient Chinese board game, just considered several thousand times tougher, if not a million times tougher than chess. And the number of possible board configurations is better, larger than the number of particles in the universe. And then it's extremely hard, and it actually needs human intuitions to solve this problem. So the machine actually beat the human being. It was actually much more like profound than humans being beaten in the game of chess. Then in 2017, Boston Dynamics did this amazing thing, and they showed that okay, fine, it's not all deep learning. Traditional control theory algorithms can actually do as much as good. So in 2017, OpenAI is a open non-profit deep learning artificial intelligence organization. Mostly focuses on a particular kind of machine learning called reinforcement learning, which Aditya is going to teach today. So they are co-founded and advised by the great Elon Musk. How many people have heard about Elon Musk? Everybody, amazing, great. So yeah, Elon Musk is on the board. So they identified this computer game called Dota 2. How many people play Dota here? Okay, more people should start playing now because machines are getting better than human beings. We need better human players. So they actually beat the world champions at 1 versus 1 Dota 2. And then you already saw Google Duplex, that was 2018. And Google I/O is coming up. So let's see what's up. Like what's the next big thing to come. So yeah, that's the. So are you people feeling interested? Like, what's the reaction? I'm feeling good. What do you think? You knew most of the things that I showed you? Yeah? Yes or no? No? Okay, great. So over the next few hours in this session, we are going to go over all the basics, and then over the next 2 days, you're going to see how people have been using these technologies to change the face of technology industry in India. And that would actually, and we're also going to start a challenge called the Chartist Chronicles tonight. So you would be able to try out your hand at making something as amazing. So thank you for now. Have a good time. So thank you. Hello? Hello? Can you please flip the sides, flip both places, here and there. दोनों दबाना, ठीक है? Yes. Whenever you switch sides, switch both of these. Why both of them? कुछ नहीं होगा, वहाँ पे पास.
Schedule के announcement.
No? Hello. So tomorrow the event is going to start at 9 a.m. at Netaji. Netaji. So please be there. Tomorrow the event is going to start at 9 a.m. at Netaji. Please be on time.
क्या क्या हुआ क्यों
Hello. Check. Hello. Hello. So, just a quick demographic check before we start. So, how many of you are first years over there? Amazing. And second years? Third years? Fourth years? Fifth years? Sixth years? Seventh years? Okay, so how many of you have like coded a neural network before or worked with neural networks or machine learning or AI? Show of hands. Very low percentage of people, right? So, cool. So this question on the top is for people who are just starting out with the AI or just know nothing about AI or deep learning or machine learning or what exactly is happening. So please pay attention. So what exactly is intelligence before we start? So intelligence for human beings is a very relative term. So for example, if a human being knows how to recognize the alphabet, we won't exactly classify it as being intelligent, right? But in the case of machines, it's different. The definition of intelligence for machines is very different. So for instance, if you log on to Instagram and check what's happening, you'll see like a lot of teenagers posting stupid photos and statuses and pound selfies and whatnot. And so that is something that I would classify as stupid in general. But like for suppose I write a program that learns how to operate social media and post such photos on social media, so maybe I would classify it as intelligence. So the bar for intelligence for machines is slightly machines is slightly lower than what we exactly place for humans. So if you look for a definition for artificial intelligence on the internet, you would be very disappointed because it is known to be very vague. So, so the authors Norvig and Peter had done a great job to actually build out how exactly artificial intelligence is to be realized. So there is no objective mathematical definition to artificial intelligence as it is to say like doing good business. Doing good business is maximizing profit, and maximizing profit is like earning more money than what you spend. So that is like mathematically grounded. But for realizing artificial intelligence, there is no such mathematically grounded definition. So all the approaches that you will see towards artificial intelligence can be broadly categorized into these four categories. So if a machine is able to do one of these four, or maybe a combination of these four, then we can classify it as being intelligent. So over here you will see four terms being repeated. One is think,
One is act, one is humanly, and one is rationally. So when I say act, I just care about how is the machine behaving from the outside. I don't care what the machine is thinking or how the machine is processing the input. I just care about its final output. And when I say think, then I'm actually concerned about what's going on underneath the hood. Right? And when I say rationally, I mean that the behavior or the thought process should be like grounded in mathematics. Like someone could be able to reason out the behavior or the actions using mathematical tools. And when I say humanly, I want to be as close as to how human beings might behave in such scenarios. So let us go through all of these four one by one. So, thinking humanly, this approach tries to model agents that actually think how the brain does. So, like I would like my algorithms to function like a human brain. So, there's a whole like field dedicated to this called cognitive modeling, or there are even very great courses going on in our campus, like computational neuroscience. So, this is one way of realizing artificial intelligence. It is to model the human brain through computational algorithms. The second way of realizing artificial intelligence is acting humanly. As in, like Anirban talked about it during test. So, if you can't differentiate the behavior of a machine from the behavior of a human being for a certain task, then it is acting humanly, and so it has passed it during test, and it can be considered as intelligent. The third way of realizing artificial intelligence is thinking rationally, or the laws of thought approach, as Anirban had like elaborated on it using first order logic. And I'm not going to go deeper into this, but this uses an entire field of studies dedicated to this topic called logic. And the last one is acting rationally. So acting rationally is I only care about the final output of my agent, and I do not care about how it is thinking. I just want that the final behavior of the agent should be rational. So which one of the approaches is like popular these days? Like which one of this do you think is like very easy to realize compared to the other three? Yeah, good. Acting rationally. So acting rationally, like designing agents that act rationally is very easier to realize. It's very obvious because like modeling human beings is a tough task. Right? And like solving mathematical equations or optimization problems is relatively easy because like we have been working on this for decades and we have come a long way. Also, thinking rationally like limits us a lot. So elaborate on this. So why rationality? Because the standard of rationality is mathematically well defined. So it is easier to design rational agents rather than human agents. And moreover, if I restrict my agent to think rationally, it will obviously act rationally because the outcome of a rational thought process is a rational action. But then I'm limiting myself to just the rational thought process. However, if I am limiting the agent to act rationally, then I don't care about how it is thinking, right? It can maybe it can start thinking rationally, or it may develop other thinking processes to realize the ultimate thing. So, designing agents that act rationally is the easiest way to go. But again, there's always a but in everything. So, borrowing elements from cognitive modeling, that is thinking humanly, helps in many cases. So, case in point, convolutional neural networks. So, this is a very popular deep learning architecture for classifying images. And the first layers of this architecture, I'll elaborate on what layers are, so don't worry if you're not able to understand the jargon. But what I wanted to take away is the initial layers of this network are inspired from the prefrontal cortex of human beings. So when people replaced normal feed-forward neural networks with this convolutional neural network inspired from cognitive neuroscience, they achieved like better accuracies in classifying images. So all of the models, like Anirban elaborated on the ImageNet dataset. So all of the models that behave well on the ImageNet dataset have the initial layers of those models have a convolution layer in them. So this is like directly inspired from neuroscience. So before I move into deep learning, I want to clarify a few misconceptions that are like really relevant about AI these days. So people these days think that AI, machine learning, deep learning, everything is exactly the same. Like they're like synonyms of each other. So like I want to like differentiate between all of these terms before we move on. So AI is what I've elaborated. It is like achieving one or more of these aims through any algorithmic process. So not necessarily deep learning or machine learning. And one of the ways to realize AI is machine learning, which is very popular these days. Machine learning is realizing AI through the aid of data. Since and why is it becoming popular these days? Because there's a lot of data available to us. Like data is being generated at a huge amount, incomprehensible speed. And also the compute power has increased like tremendously over the past few years. So now A, we have a lot of data, and B, we have a lot of computation power to process it. And every machine learning algorithm that you will encounter like behaves like its accuracy increases as like the more data it consumes, the better it gets at doing something. So since we are generating a lot of data and we have like reached like superhuman, like supercomputers in computational power, so machine learning is very popular. And what is deep learning? Deep learning is using a very specific machine learning algorithm in neural networks to achieve intelligence. So like nowadays, like neural networks require even more computation power than general machine learning algorithms, and they are able to model very complex functions, and thus are able to achieve very high accuracy, very complex tasks, something that normal machine learning algorithms fail to achieve. So due to the increase in compute power and data, nowadays deep learning, that is using neural networks to solve intelligent tasks, is becoming very popular these days. So reiterating, AI is a superset. Machine learning is a part of AI, and deep learning is a very specific part of machine learning which deals with using neural networks to solving intelligence problems. I hope this is clear. And anyway, do not think that deep learning is the final solution to realizing artificial intelligence. It has just become popular these days because we were not making a lot of headway using traditional algorithms. And when people started using deep learning algorithms, they made slight progress. Like, it was like better than the past. So like everyone is jumping into the deep learning bandwagon these days. However, this doesn't imply that deep learning is the ultimate solution. We are still very far away from realizing true artificial intelligence. So it can be the case that 30 years later, some other thing is hot or like deep learning goes away. So just don't think that deep learning is the final solution. It is very popular these days. So without wasting more time, let's dive into what deep learning is. So as I said, deep learning is all about this fancy thing they call a neural network. And to a beginner, it sounds really cool, like neurons and shit, and complicated and scary. Why scary? Because like jumping into this machine learning and deep learning requires you. So jumping into machine learning and deep learning requires A, knowing the theory behind it, and B, like learning to code. And these are two very big steps for someone who has just entered engineering college. Like I used to really fear like writing programs and all in my first year. So like this is very complicated for a beginner. Sounds complicated, but it isn't. It's very easy, and I'm going to prove that it's very easy to like understand what a neural network does and like write code for it. So don't get married inside out. We will like unravel the mystery behind neural networks. Yeah, it is. So let's learn how to build a very simple neural network, a very basic idea behind a neural network, and do cool things with it, like recognizing handwritten digits and recognizing spam in your network. So like really cool things can be done with a very simple neural network architecture that I'm going to talk about today in this talk. So the first step is how do I represent my input? So it's pretty easy. Each input instance to a neural network is encoded as a vector of floating point numbers. I hope all of you know what a vector is, right? We have studied it in our first year, even in our JE days, right? So vector is just an array of numbers. That's it. And matrices are 2D arrays of numbers. So I think that is pretty clear. So for our first task, that is like classifying digits. So an image is nothing but a bunch of pixels. So with each, like it's divided into a grid, and each pixel is associated with numerical value specifying its intensity. So if there's a high numerical value associated with the pixel, then it will be towards 5. and if it is low, then it will be towards black. So it's pretty evident in the picture that the black regions of this letter A are close to 0, right? They have a low value, and the white portions of the image have a intensity value of close to 1. So to represent this image as an input to my neural network, I will do a very simple flattening operation and flatten out this 2D matrix into a 1D matrix. So it's pretty easy. So you can see that this 3 cross 3. So for example, if I have a 3 cross 3 image, then it is flattened into this particular vector. So each image of my dataset is a 27 cross 27 image. So naturally, I have a 784 dimensional vector for each image. And for e-waves, because there is no direct mapping to numbers for a language, for a particular text, I use a technique which is called bag of words. So bag of words is a very simple model to vectorize a sentence. So what we do is we fix a vocabulary initially, like I'll fix my word set. These are only the words that I'll consider. So anything that is out of vocabulary is not considered at all. And to each word, I'll assign a unique integer between 1 to the size of the vocabulary. So every word has a unique index. So and to each email is a now d-dimensional vector with the value at the index corresponding to a word set to its frequency in the email. So let's divide. So for this particular sentence, if I want to vectorize it, so I have a d-dimensional vector, and so focus on the index 0 that corresponds to document. So the word document appears once in this piece of text, and so there's a 1 entry corresponding to that index. So animal doesn't appear in this sentence, so it's 0. Similarly, model appears 2 times, and so on. I hope this is clear. This is very easy to understand. So can you think of any obvious disadvantages of both the representations? If anyone can answer this question. So, question for Anna 221. So, can any of you think of any obvious disadvantages of both the representations?
You cannot get all your words.
Yeah, exactly. So, do we have goodies for this person? So, definitely. So the order of words is lost in this back of words representation, right? So if I jumble this particular email, then it doesn't make sense. However, for my neural network, the input will be exactly the same. And can you think of any limitations of the approach that I used to vectorize the image in the recognizing the digit space? Anyone? NR221. So, NR222, if you're listening, can you answer this question? So, is there a problem with the representation for the digit space? So, let's move on. I think there are answers to this. You wait for them to answer. It's actually for them because we are unfair for them. Okay, let's move on. So I think we're clear with the input, right? So next step is constructing my neural network architecture. So this word architecture is thrown around a lot. Sounds pretty cool, but it's just deciding what layers you want to put in a neural network. So layers are the basic building blocks of a neural network. So a neural network is nothing but a bunch of layers stacked on top of each other, like Lego blocks. How many of you know what Lego blocks are? Cool. Amazing. So it's like just choosing different types of layers according to your task and stacking them on top of each other and being going on a neural network. As easy as that. So let's understand what a layer is. So Anirban elaborated on this ImageNet, right? So ImageNet was a challenge for image classification. And nowadays, deep neural networks in this competition. So this little girl is crying because a shallow network didn't win the competition. So layers. So Deep learning practitioners use several kinds of layers, like the fully connected layer, just bunch of jargon, the computation layer, LSTM, etc. So in this particular lecture, I'll just talk about the fully connected layer. That is the very basic layer of a neural network and is like will be present in any neural network that you encounter. So if you want to know layers, the first thing that you have to know is the fully connected layer. So each layer consists of some parameters. A fully connected layer consists of two parameters, the weight matrix and the bias vector. I think we know what a matrix and a vector are. So a layer takes as input some vector or matrix, does some mathematical operations on the input with its parameters, and produces an output vector or matrix. As simple as that. Will take as an input a vector or matrix and will produce as output another vector or matrix. Right? So the fully connected layer consists of two parameter sets, the weight matrix and the bias vector. So the operations are standard matrix multiplication and addition. My input is x, which is a vector, and I multiply x by w and add the bias vector p. And I hope it should be clear to anyone who knows matrix multiplication that the output would be a vector. Right? Do you agree with me? The output of this operation would be a vector. So NR221, little question for you. So the dimension of my input, that is x, is t. Okay, and I want my output vector to have a dimension of 4. So can anyone tell me the dimensions of the weight matrix and the bias vector? Like, could there be anything, or is there a constraint placed on the dimensions of the weight matrix and the bias vector because of it amounts? Now, E cross O for weight matrix, and for the bias vector, anyone else? Yeah, correct. Give this guy. Raise your hand. So the way I've defined my operations is W x plus V and not x W plus V. So that is why the dimension of my weight matrix is O cross C and the bias vector is O. I hope this should be clear to everyone, right? So now I'll tell you a little secret. Now I'll tell you a little secret. And when you know this secret, you will be able to design your first architecture. So this complicated word that people practicing deep learning throw around, you will have your first architecture ready with you. So this secret is that when you're designing a network that has the final layer as a fully connected layer, then the dimension of the output of the final FC layer of a neural network is equal to the number of unique input classes. So I'll elaborate on this. So for the handwritten digit recognition task, there are 10 classes, right? The number is 0 to 9. And for identifying spam email, I have 2 classes. So if I am designing a neural network to solve this task of recognizing handwritten digits, then the dimension of the output vector of the final fully connected layer should be 10. And for the spam email, it should be 2. So another question. So if I'm designing a neural network with a single fully connected layer for classifying handwritten digits, so I know that each image is 27 star 27 dimensional. So what should be the dimensions of the weight matrix and the bias vector of this fully connected layer? I hope the question is clear, right? So I told you a little secret about here. Repeat. 10 cross 27, right? Anyone else? So, 27 star 27, that's like 784, right? Don't get confused. No. 9 cross 729. 9 cross 729. 729. Close. Do you understand what this 27 star 27 means? So it means that the image is 27 cross 27. It's a 2D matrix of dimension 27 and 27. So first you have to reduce it to the input. That is 784 dimensional. And then you design your layer. Sorry, 729. So correct. What did you answer? 729.
Now,
For the weight matrix. And bias vector? Yeah, correct. Sorry, my bad. Good days for this guy. Just made a slight error in the slides. Should be 729 over here, and the bias vector should be 10. So, congrats. So, I've designed your first year of architecture. Yay. Okay, whatever. Silence. So, for any image, the output of my one-line neural network is a 10-dimensional vector. And this output I'll call scores or logics, right? So now I'll try to convert these scores into a probability distribution over the classes. So the higher the score is, the index with the highest score is my prediction for the neural network. So in this case, I would want that the 8th index of this neural network should have the highest score. So I'll do a score transformation now. I'll convert these scores into probabilities. So one of the ways of converting unnormalized scores into probabilities is doing this. Like you exponentiate all the scores and then normalize them by the sum of the exponentials. So now we have a probability distribution. And an advantage of this method is that scores could be negative, but probabilities are always positive. So when you exponentiate any number, you always get a positive number. Right? So this is one way to convert unnormalized scores into a probability distribution. So this is like 3 scores. So according to this output, my neural network is classifying whatever input there was to the first class with a probability of 0.7. I hope this is clear, right? This is pretty easy. So my expectations is I'll pass this image into my neural network and I'll get this output, right? With the 8th index as 7. 8 because the first index corresponds to the digit 0. So the 8th index should be 1. Or at the very least, it should assign the maximum probability to the output being 7. I hope this should be very clear to all. So how would I go about realizing this? So it's easy. Assume so. I have to find the most suitable weight matrix and bias vector. That is the parameters. I call these the parameters of the layer, which maximize the prediction accuracy on my data set. Right? This is all that I have to do. I have to just find the most appropriate weight matrix and bias vector pair that will maximize the prediction accuracy of my data set. Cool. Fair enough. But then, how will I go about doing this? So again, a slight error over here. This should be 729. So I have 7290 parameters in my weight matrix and 10 parameters of my bias vector. So it's a very huge search problem. And solving this problem is very difficult. So before we move on, I wanted to realize something beautiful. So this seemingly tough task of classifying handwritten digits. I just have to find a bunch of numbers that are giving me maximum accuracy of my data set, and that's it. Then I'm done. So we have reduced a very abstract problem of classifying handwritten digits into a search problem in the parameter space. So almost all algorithms that you find in an AI textbook deal with certain variations of this search problem. So there's a very beautiful textbook on AI by Peter and Norway. The people who gave those 4-fold definition of AI, I would recommend that you go through it. It will give you a really good overview of what AI actually is. And then you will find that almost all of the chapters deal with certain variations of the search problem. And this, what I'm trying to solve, is also a search problem. I'm searching in the parameter space and I'm finding the most appropriate parameters that fit my data. So the first approach that jumps to your mind is take many different random initializations of the parameters and choose the one which gives you the best accuracy. So this approach is pretty shitty because The method of searching over is unguided. Like I'm not using my data to improve. Like let's just say I've come across some parameters, and I'm not using my data to improve those parameters. I'm just using my data to check how good they are. So it will take a very long time for me, like a very long time to come across some good parameters. So like to give you an idea, let us say that I reduce my parameter space, all the parameters, to be binary digits, 1 or 0, and not decimal numbers. So still, the problem of search is very huge. Like there are 2 to the power 7290 plus 10 possible weight and bias matrices. Right? I hope this is clear with everyone. Like I have to search through such a humongous set of weight matrices and bias vectors before I arrive at something good. So this is called intractable. Intractable is a word that is used for algorithms that cannot be realized in good computation. Like they will take a lot of years to actually come across to a solution. So ideally, I would want a method where the data set guides me towards the optimum parameters. Right? So here's where the final building blocks of a neural network will help. That is the loss functions and gradient descent. So this is my loss function, J, and the theta is the set of all parameters. And looks complicated, but I'll describe what this actually is. So first of all, my data set is a pair of tuples. Like it is a collection of tuples xi and yi, where xi is the ith input. In this case, the image of 7. In yi, it's the label 7. Right? My data set is just a collection of these input and its labels. So let us say my network assigns probability p to yi on input xi. Then I define my loss on this particular data point as minus of natural logarithm of p. Now, loss is something that you generally try to minimize in your day-to-day life, right? So I'll just show to you that minimizing this particular loss is actually making us move towards higher classification accuracies. Because let us say the p is 1, that is like I've assigned probability 1 to the correct label. Then I'm doing correct classification. So my loss is 0 because log of 1 is 0, right? And if I have assigned probability 0 to this input being yi, that is the most incorrect classification, and my loss is infinite. So I hope you're with me when I say that reducing the loss on this data set or any data point is equivalent to achieving higher classification accuracies. Like it should be very clear to everyone because this is where we'll build and study gradient descent, which is a method to find optimal parameters in a tractable amount of time. So this should be very clear to everyone. So nothing. So since there are many data points, not just one, there are a lot of data points. So I just sum this loss over all values of I, not just one xi, yi, like the entire data set. And if I'm getting lower losses, then that indicates higher classification accuracy on the data set. Right? I hope this is very clear to everyone. So I'm changing my objective from getting higher classification accuracies to minimizing this loss function. Okay, and both of them are equivalent, and I hope this is very clear to everyone. So I've changed my task, and now my modified task is finding parameters that minimize a loss function. But then again, I have not made much progress. It's just the same problem stated in another way. I'm modifying it like this, like this. So let's see how this helps us. So a key thing to realize is this loss function, as I've defined it in the above slides, is a differentiable function of the parameters of the neural network and my entire data set. Right? I hope this is also very clear to everyone. First of all, this is a function of the parameters and the data set, right? Because this is taking as input all of that stuff. And it is also differentiable. You can convince yourself that it is differentiable. I could give a formula proof, obviously, because there is no time. But you have to realize this fact that this loss function is a differentiable function of the parameters of the neural network and the entire data set. So, when we have differentiable functions, a very common algorithm to find minimas, to find the set of parameters that minimize the value of this function, is gradient descent. So what gradient descent does is, suppose that the loss is a function of just one variable. So in our case, the loss is a function of 7920 parameters and the entire data set. There are a lot of variables, but for sanctity, let us assume that my loss is a function of just one variable. So what I do is, I want to find the value of w, this variable, that minimizes the loss. So First, I'll initialize it randomly, and then I'll calculate the gradient, that is delta loss by delta W, the partial gradient, and I'll repeat this operation that is written in the course. Like I'll move against the gradient. So if my gradient is like positive, I'll decrease the value of W by this amount, alpha times the derivative. So alpha is called the learning rate. And this is like, you can set it to any value. If it is very high, then you have large fluctuations of W. And if it is very low, the W will move slowly towards the blue minimum. I hope this algorithm is clear to everyone. I'm just iterating it. You could say that, but if the value of alpha is very small, then you will take a large amount of time to reach the. So I hope this algorithm is clear to everyone, and that if I apply this iteratively to this particular graph, then I'll reach the local minimum, right? Because I'm moving against the gradient, and ultimately I'll end up at this global loss minimum for this particular function, right? And alpha is something that you have to set on your own. It is an engineering problem, not something that can be decided mathematically. So very large values of alpha can land you in trouble, and very low values of alpha would take very slow conversions. So gradient descent is easy. So you randomly initialize all the parameters, and then you just calculate the partial derivative with respect to each parameter, and then do this operation iteratively.
Guys, do you want to know how Gary Kasparov was defeated? Do you want to know how humanoid agents are trained? Do you want to know how OpenAI defeated Dota 2 champion? Yes. Be right back in 10 minutes here. This is a 10 minutes break. Come back in 10 minutes, you will know all the answers. So the time is currently 9:35. Be back here at 9:45, okay? Sharp 9:45. We'll resume the session at 9:45.
Now, अगर possible हो तो like लोग बोल रहे हैं compromise करो and also यहाँ से भी वही
and then take a step in the opposite direction. So if it is positive, I take a step in the negative direction, decrease the habit, and by and amount that is the gradient at I and at the same time like us. It can be everything, it should be a small number, but it depends on practice. So we raise against the gradient application. So this is the way of minimizing function. So over here it just didn't look like but in the loss function I have multiple parameters, 7, 9, 2. So the algorithm is I find the derivative with respect to each parameter, partial derivative, and then I reduce the parameter against the direction.
ये लोग मुझको बोल रहा है कि आवाज थोड़ा कम है इसमें ठीक है आवाज इधर से बढ़ता है क्षमा क्या
मैं उधर बैठा हुआ ऑफिस यहाँ पे वाले किसी को बोल रहे हैं वर्तमान क्या
ठीक है वो कर लेगा क्या
मैं बता दूं कौन सा है यहाँ पे
ठीक है देखो वहाँ पे आखिरी 2 बटन है ना वॉल्यूम आप वॉल्यूम डाउन नहीं नहीं यहाँ पे ठीक है तो मैक्सी है कोई फर्क नहीं
हाँ हाँ वही वही आप मेरे को देखने पर मैं यहाँ बैठा हूँ
अब बेसिकली यहाँ तो कुछ समझ आ रहा है जब डेटा में जाते हैं
ये सब तो तेरा सबको मैंने एक्सपोनेंशिएट कर दिया some positive numbers are equal probability 0 वाली क्लास
पहली बार सुन रहा हूँ तो फील नहीं आ पा रही कि स्पोर्ट्स के लिए स्पोर्ट्स के लिए जनरेट हो रहा है क्या करूँ अगर मेरे सीधी हो
रिसोर्सेज बता
और रिसोर्सेज
अचानक से माहौल
ये कैसे बता देगा
थोड़ा सा वॉल्यूम कम है ठीक है और शुरू करते हैं 5 मिनट
ठीक है हाँ तो यहाँ से लोकेशन यहाँ से मैं उसको सब लोग
कौन सी स्लाइड रिपीट कर रहे
Guys, we are about to start. Please call your friends. Hesitate not to
ब्रेक देने के बाद इतने लोग रुके तो अच्छा लग रहा है। ब्रेक दिए थे ताकि अनइंटरेस्टेड लोग निकल जाए, फिर भी अच्छी बात लगता है वहाँ पर भी खड़े
Hello. So, I think there was some slight audio issues and people at the back were able to listen, right? Hello, people at the back. Hello. Is it audible now? Should I lower my voice or is it okay now? Hello. 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 This is fine, right? This is fine. Okay, cool. So, like, I'll rewind from over here. I think you guys are lost me after this, right? And it became slightly complicated. So let us start from here. I'm audible, right? Okay. So now I designed my neural network that gave as an output a 10-dimensional vector of scores, right? It was clear up till now. Okay. So I want to like convert these scores into a probability distribution over all the classes. So these scores could be like random values, random negative values, random positive values, and the class with the highest score is like the label that is being assigned by the neural network to the input. Okay, so to convert these values into a probability distribution, what I do is I exponentiate all the scores and then I divide it by the sum of all the exponentials. So when I exponentiate these numbers, I obtain positive numbers, and when I divide them by the sum of the numbers, I obtain a probability distribution. Right? It's audible now, right? More louder. So when my input is 7, I expect an output that is like this. So my neural network should ideally output this particular probability distribution, where it is 1 at the index that corresponds to 7 and 0 everywhere. Okay. Or at the bare minimum, in this probability distribution, the index corresponding to 7 should have the maximum probability value, right? So if it is like this, then my neural network is functioning correctly. It's audible, right? I think I figured this out. So how will I do this? So my task is to find the most suitable weight matrix at the bias vector. That is the parameters which maximize the prediction accuracy on the data set, right? But how will I go about achieving this? So my weight matrix has like 7290 parameters. This is a misprint, I'm really sorry. And the bias vector has 10 parameters. So I have to find a bunch of like this 7950 or something parameters that give maximum accuracy on my data set. Like, I hope this is clear. So before we move on, I want you to realize something beautiful, something that is very elegant about this solution. So we have reduced this very abstract problem of classifying handwritten digits to a not a simple, but at least a search problem in the parameter space. So the solution is just to find a bunch of numbers that give maximum accuracy on my training data. So almost all algorithms that you may find in an AI textbook deal with certain variations of the search problem. So there's a textbook by Peter and Norman, the guys who gave that 4-pronged definition of artificial intelligence that like deals with AI and has like a lot of chapters on various approaches in AI textbooks. So it is recommended that you go through this textbook. Yeah. Peter and Norvig, P-E-T-E-R, and Norvig, N-O-R-V-I-G. So one solution to this problem is like take like many different initializations of the weight and the bias like matrices and choose the best one. Okay, this sounds like maybe this is pretty simple, but there is something fundamentally wrong with this approach, right? This method of searching is unguided and intractable because it will take a lot of time for me to to come to the right, like the optimum bias vector and the weight matrix. So just to give you an idea, let us say that all the values in the weight matrix and the bias vector could be just bits, 0 and 1. So even in this very simple configuration, there are 2 to the power 7, 8, 5, 0 something possible initializations of the weight matrix and the bias vector. So you can see the humongous nature of the search problem even in the reduced version, let alone having decimal numbers in places of the parameters. So I want to have a method where the data set guides me towards the optimum parameters rather than just shooting arrows in the dark and hoping that at the right parameter space. Cool. So over here, the final building blocks of our neural network are right. The loss function, which caused a lot of chaos as I was notified by these people. So I'll go through it very slowly, what the loss function is and how I use my loss function for this algorithm called gradient descent to come across the right parameters. So I define my loss function like this: j of theta. J is the function, and theta is set of all parameters. And this seems very complicated when you look at it, but like step by step, I'll unfold what this loss function is and how I use it to obtain the right parameters. Okay. So my data set is a collection of images and the correct label. So xi is the image and yi is the correct label for this image. So xi is this beautiful image and yi is the correct label, that is 7. Okay. So as far as the network I have designed, it assigns probabilities to each class. So for this input xi, the output of my neural network is a probability distribution over all the classes, right? And it must have assigned some probability p to the correct class of this input, that is yi, that is 7. So there could be a probability of 0.3 assigned to it being 7. So this p is 0.3 in this case. So my loss function is minus of natural logarithm of this probability. Now, whenever there is loss, we try to minimize it, right? So in this scenario, it makes sense because if I'm classifying this particular image correctly, then p is 1, right? And natural logarithm of p, that is 1, is 0. So my loss is at the minimum value of 0. And if my probability is 0, that is the most incorrect classification, then my loss is infinite. Right? You can see this, positive of infinity. So minimizing the loss function is equivalent to achieving higher accuracies on the data set. So xi and yi was a single data point in my data set. Right? So there are multiple such tuples, x1, y1, x2, y2. So I do nothing but sum this minus log of p over all of these points. Right? And this is my loss over the entire data set. I hope this is like very clear to everyone sitting here. Right? Am I audible in the last rows? It's the final check. Am I audible? Okay, cool. So I hope this is very clear. And if I'm minimizing my loss function, then I'm moving towards achieving higher accuracies on my data set. I hope this is also very evident from the previous discussion. So I can see heads nodding, and this is like very encouraging. Thank you. So a lower value of the loss function indicates higher classification accuracy on the data set. So finding parameters that minimize our loss function is the key to solving this abstract problem of classifying results. So till now I've done nothing. I've just reframed this problem of achieving higher accuracies on the data by substituting it with the loss function. So till now I've achieved nothing as far as finding the correct parameters go. So before we move on, I wanted to realize this beautiful fact that this loss as defined is the function, forget differentiable, is a function of the parameters of the neural network and my entire data set. Right? This is pretty obvious. And like you have to convince yourself or believe me, because this is not a place to give a formal proof. But this loss as defined is a differentiable function of the parameters and the entire data set. And when I'm trying to like optimize a quantity which is differentiable with respect to certain parameters, like I have many approaches. For example, like we have studied like finding minimas in our JETs, right? Differentiating a function and equating it to 0 and finding points which satisfy this equation. So like I have many computational methods that can achieve this particular objective. So one such method that works for general functions or does a great job, not the most suitable job, let us say, is the gradient descent algorithm. So For now, assume that the loss is just a function of a single parameter, okay, not a bunch of many parameters, W. And this is how the loss goes. This is the function, and I want to like find this particular value of W that minimizes this loss function. Cool. So one way that we have studied is to differentiate this function and equate it to 0 and find W. So another way is like take a random guess of W, like what could be W, and find the derivative of this loss function at this particular value of W and reassign the value of W to W minus alpha, that is some constant, times the derivative. So I want you to convince yourself that if I keep doing this repeatedly, I'll arrive at this minimum point that is indicated in the figure. Right? Because if the gradient is positive, then I'm moving in the left direction. If the gradient is negative, suppose I'm in the left portion of this curve, then I'm moving in the right direction. And ultimately, I'll arrive at this particular point of local minimum, assuming a suitable value of alpha. Right? I hope this is very clear to everyone. So, gradient descent is a way of optimizing a function, optimizing a differentiable function of parameters. So, over here, I just had one parameter, that is W. But the original loss function is a function of several parameters, right? Like around 7,000, 8,000, whatever the number was, parameters. So, for that, what I'll do is, I'll first randomly initialize all the parameters, like I randomly initialize W, and then I'll just do this until convergence. So, for let us say for a particular parameter, theta j, that could be a particular entry in the weight matrix, or it could be a particular entry in the bias vector. So I find the partial derivative. I hope everyone knows what a partial derivative is, right? You assume that all the other parameters are constant and just differentiate the function with respect to this particular parameter, and you do this again repeatedly for all the parameters until you converge, like until the derivative becomes 0, or until you have achieved the significantly low value of the loss function. Okay, I hope this is clear to everyone. Pretty simple. So there are a few problems with gradient descent, as many of you might have like realized. So if let us say I want to find the global minimum for this particular loss function, which is a function of like a single parameter. So if I run gradient descent, I'll arrive at the local minimum. I hope this is clear. This is very simple. So another problem is it is very slow. Can anyone tell me why it is like very slow doing this gradient descent like the way we have discussed?
Because we respect each parameter. Yeah. You have to do respect each parameter. Right? Partial derivative each parameter.
Okay, but like if I have around 8,000 parameters, it's simple. Like a computer can do 10 to the power 5 operations in like a fraction of a second. So that's not a problem. But yes, we're moving in the right direction. Yeah, yeah. But like having high values of alpha may lead you to like diverging. So that's not the solution. But
as we approach the minima, the value we are subtracting also becomes very small. So as we are approaching closer and closer, we are very small steps. So
okay, but
because slope is approaching 0, so as we are approaching,
I get your point, but there is an even bigger like issue at play. Like, this is a very small issue compared to the issue that we are missing out on. Yeah. Last. Okay, I think we are missing a very important point. That's okay. So moving back. Yeah, over there. This fourth point, focus on the fourth point. So since there are many data points, I have to sum this loss over all values of time. Okay. So let us say that I have like 60,000 images in my data set. So to compute the loss function once, I'll have to like sum over all of the images, calculate the probabilities, and like calculate the final loss. So I will iterate to 50,000 images to obtain the gradients and then change the parameters by single step. Then I iterate through the 50,000 images again to calculate the gradients and to like obtain new values on the parameters. So this is a very slow process, and like this is a very like, huge deal breaker with this gradient descent thing, that you have to iterate over all of the data points in your data set. So Yeah, this is the problem. You need to iterate over the entire data set to calculate the loss and the gradients, and you have to do this multiple times until you reach a suitable value for the parameters. And in this data set, this is called the MNIST data set for numbers. There are over 50,000 images. So you can calculate the time constraint that this method imposes on a problem. So I need to find something that speeds this process up. So here comes stochastic gradient descent. So instead of summing up over all of the data points, I'll randomly sample a small data set, small subset of the data set each time, which I'll call the mini batch of the data for calculating the gradient. So the gradients that are now calculated are not exact, but are an approximation of the net gradient. So instead of taking 50,000 images, I'll just take like 32 or 64 images to calculate the gradient, randomly sampled from the data set. So for the MNIST data set, a batch size of 32 works. So imagine the speed up obtained when you use a batch size of 32 instead of 50,000. Like you could divide these two numbers and obtain an estimate of the speed up. So as to how these gradients are calculated with respect to each parameter is beyond the scope of today's discussion. But all of you who are curious can search for this thing called backpropagation, which is a very efficient way to calculate all these gradients. Okay. So congratulations. Now we have designed a neural network and we know how to train this neural network to achieve like higher accuracies on my data set. So just a few more things before we start training our neural network. So to check whether a neural network is performing well, I classify my data set into two parts. One is the training set, one is the validation set. So the training set is used to calculate the gradients and the validation set is left untouched. And once my neural network is trained, to check how good that neural network is, I run it on the validation set once and obtain the accuracies. Because ultimately I want my neural network to classify images that are unseen during its training, right? So I keep a certain section of the data set reserved that is not used in the training procedure and that is used to check how my neural network would perform on unseen data. Like that is like a more suitable test than reporting the accuracy of the training data. Also, last but not the least, I mentioned that neural networks are all about multiple layers, like stacking multiple layers, and till now I've only talked about a single layer. So what about multiple layers? So let's say two fully connected layers. The output of the first is the input of the second. It's pretty easy. So I think this equation is very obvious. So for the first layer, my parameters are W1 and B1. For the second, W2 and B2. The input is X and my final output is this. So W2 times the output of the first layer plus B2. I hope this is very clear. But do you see the issue with this approach? So I'll not ask this question because we're running short of time. I'll just directly tell what's the issue. So when you solve this expression further, you'll arrive at this. So this is like having a single layer with the weight matrix as W2 into W1 and the bias vector as W2 times B1 plus B2. I hope this is very easy to understand. And so stacking multiple layers. So stacking multiple fully connected layers is equivalent to just having a single fully connected layer. So the solution is to introduce non-linearities between the layers. So here is a very common non-linearity. We studied one non-linearity, which was the softmax function, which assigned probabilities to the scores that my neural network outputs. So this is another non-linearity that is commonly used between layers, which is called the ReLU function. So ReLU function looks like this. So the output of a ReLU function is 0 if the input is negative, and it is the same number if it is positive. It is identity for positive numbers and 0 for negative numbers. So for instance, the ReLU of this vector would be this number. Like the -5 and the -6 are reduced to 0. So now my output is W2 into ReLU of the output of the first layer. The output would be a vector plus the bias term. So a two-layer neural network with a non-linearity is able to model more complex functions than a one-layer neural network. This is something that you'll have to like take for granted. I can't explain this right now. So things that I didn't talk about are hyperparameters and then tuning, overfitting and underfitting, and regularization. These are some terms that you would have to like Google on your own, and these are very important in deep learning, which I don't have time, unfortunately, to elaborate on these terms. So that's it. Thank you. Please note these down. Yeah, so there's a short demo on like implementing a neural network on the handwritten digits dataset. So there's a small demo that training a neural network that we have discussed, a one layer and a two layer neural network on this dataset of handwritten digits, and we'll see how that works. Just don't get scared by the code. Like if you practice Python for like 2-3 months, you'll be able to understand what's going on. I want you to like focus on how easy it is to train a neural network by just like 50 to 60 lines of Python. So right now I'm just loading the data set. So my data set is like a bunch of 15,000 images, and each image is already flattened down as we have discussed. And these are the intensity values for each pixel. The values are between 0 to 255, and I've displayed some of the values over here. So let us go through this code. Not focusing on the code right now. So these are some sample images from the data set. So this is a 7, and this is a 3, and so on. This is a 0. These are all handwritten by some people, like long ago. So first step is I'm splitting my data into the training set and the validation set. So train X is my training images, train Y is the labels of the images, and valid X and so on. So this is how easy it is to define a neural network in a very standard library. This is PyTorch or Python, and these are the two neural networks that I have defined. This is the first one is the single layer classifier, the one layer neural network. As you can see, there is a single linear layer over here, and I'm returning the log of the sort method. Just to focus on the specifics. When I said how easy it is to code a neural network on these typical libraries like PyTorch and TensorFlow and all. So a key advantage of these libraries is that they do calculate the gradients automatically for you. So you just have to design your neural network, and you can rely on PyTorch to calculate the gradients in the gradient descent for you automatically. They use this backpropagation algorithm in their backend. So the first function is a single layer classifier. So as you can see, I'm returning the sort max of the linear layer. And in the second function, I'm passing this through ReLU, and then I'm passing it through another linear layer. So here I've kept my batch size is 32. So let us change this batch size to the entire data set. And we'll see how slow this is. Let us keep the batch size as the length of the data set. Here I'm defining my two models, and let me train the first model first. So on the left, it is printing the loss, and on that is the J theta thing that we discussed. And on the right is the percentage accuracy in the validation set that I kept preserved. That is not helping the training. So you can see that the accuracies are increasing very slowly on the validation set. So let me pause this and run stochastic gradient descent, where I change my batch size to a very small number, like 32. I initialize my networks again, and now you see how fast. Just remember these numbers. Like it is reaching 90 after the 51st iteration. And when I run this now, see I'm at 89 at my first iteration only. So this is stochastic gradient descent versus normal gradient descent. Speeds up your training by a long margin. So I'll pause this and train my two-layer neural network. So just with the same batch size. So you can see the two-layer neural network achieves higher accuracies than the one-layer neural network. That is 94, 96, and if I keep training it, it will increase to 97 and reaches a maximum at 97 or 98. So you see how easy it is to build a classifier that recognizes handwritten digits. Like it only took me hardly 5 to 10 seconds to train this entire thing on the MNIST dataset. So let us see some outputs. So here I choose random images for which the prediction of my one-layer neural network is wrong and the prediction of my two-layer neural network is correct. So for this image, my one-layer neural network thinks that it is an image of 3, but my two-layer network correctly classifies it as 2. Again, 9, and my one-layer neural network thinks it is a 4. Now it is very easy for even a human being to be confused whether it is a 4 or a 9. Like we are confused a lot of times whether the number is a 4 or a 9 because they look very same. So, but a two-layer neural network is able to like understand what a 9 is. Similarly, this answer.
Hello guys, I am Gurudi Aditya, fourth year computer science department student. So I'm gonna talk about reinforcement learning. You see the black niggas going crazy over reinforcement learning. Let's all go high on AI. What do we want to do here? We want to create agents that learn like humans. So for that, what do you need to know? What do you need to know? You need to know how humans learn. How do humans learn? Let's start with your daily life. You experience situations in life. So this is a happy situation. This is a not so happy situation. What happens is your brain creates a happiness factor for every situation you experience daily. It's called a dopamine spike. Anybody heard of it before? So once all your experience is stored in your head, I'm sorry, the live stream went off. Let's get back to the meme. You see black niggas going crazy over it. We want to create agents that learn like humans. So in order to achieve this goal, you need to know how humans learn. How do humans learn? So this is a typical guy's life. He'll be happy with friends and booze. He's not so happy with tripping over the bicycle. So this creates a happiness factor with every situation you experience in your brain. it is registered with something called a dopamine spike. Every incident will have a tag of dopamine. Now, once all the experience is stored in your brain in a single day, you go to sleep in the night. Once you sleep, your sleep cycle will have something called non-REM sleep. So your daily experience will be recovered from your hippocampus, which is a section of the brain, and your brain trains on your experience. It will learn which actions of yours led to happy ending, and this is also important. It will learn which of yours led to unhappy ending. And your stronger emotions of your day are learned better. That is the reason you remember better emotions and stronger hatred than weak emotions. Now, this is how we learn. Now, how do you capture this in a computer? How do you model this in a computer? Each situation, consider it as a sequence of states. The happiness factor I mentioned, the dopamine spike, it is called reward. In an episode, I mean a sequence of events. You move from one state to another with some probability associated with it. It's called transition probability of states. Am I clear? Is it audible? And with transition probability. So we will learn what action to choose at every state, and it's stored in something called policy. Your policy is something you stand in a situation and your brain tells do this action because your policy is telling you to do this action. Policy is the probability of choosing an action at a given state. I'm standing here right now. I can throw the mic at you. I can run from here. I have many options for doing actions, but I choose the right action because the probability of doing the right action is higher. I'm trained that way. After an action, you take observation from the environment. So I'm speaking right now and I'm observing you. If you guys nod your head properly, I would know that's good feedback. This is my observation with the environment. Now, how do you interact with the environment? Things I said just now, they are in a vague sense. Now, in a mathematical terms, I define AT is the action at a time instant t, RT as the reward I obtained from the environment, OT is the observation from the environment, and ST is the state at a time instant t. Now, this is the mathematical modeling. Now, how do you learn your policy? As I said, policy is what decides your action at a state. How do you learn it? What do you do to learn? You generate a lot of examples. You run into random problems every day and you learn something, right? Similarly, you have to generate a lot of episodes by interacting with the environment, represent this in a compact way, and learn the policy. Simple as that. Clear? Is it clear? Yeah. So there are two kinds of learning. One is called model-based reinforcement learning. The other is model-free reinforcement learning. How many of you still remember about transition probability? Are you guys paying attention? It's transition probability. How many of you remember? Transition probability is a probability of a transition from state A to state B upon doing an action. Suppose I display this mic here. This is a new state and my action is moving my hand. So I have a probability of doing this. This is a transition probability. Alright? So these are the two models, two learning models. One has transition probabilities, one does not have transition probabilities. As you know, most of our stuff we deal with have assumptions, like professors say, assume this, assume that. I'm also going to state an assumption right away. It's called Markovian property. My next state from this state is depending only on my current state. Me being here and talking depends just on my previous immediate state, standing here, not on the state in the morning, I am eating my breakfast. This state is irrelevant to my current next state. This is a simple property. So the equation shown here is probability of going to state st plus 1 from st is equal to the probability of st plus 1 with all the previous states happening. So or s1, s2, s3 till st minus 1, there does not make a difference of this probability. As I already described, policy is what tells you what action you need to do at some given state. So it's a probability of taking an action. The representation I'm using here is pi is the probability and at is the action, given st is the state. This is a value from, what is the range of this value? Right, 0 to 1, it's a probability. Now I'm going to define something called value function. Now you are in the beginning of an event. Value function captures your estimated reward. After this event completes, what is the expected reward I get at the end? Or what is the expected reward of the cumulative rewards? Anybody has any doubts on this? Is the definition clear? It's the expected reward I get in the future. Now there is a bunch of mathematics going on here. Don't be scared. It's pretty simple. So value of a state S. Suppose I'm in a state S. It's the as I told. It's the E is the expectation. GT is the return. Cumulative discounted reward. Don't be freaked out. So GT is RT is the reward at time instant T. Now in a future time T plus 1, T plus 2, T plus 3, T plus 4, I do not want those rewards to affect my current decision. Do you like to have a life where your current happiness is more important or your 10 years happiness is more important? Both of those matter, right? The current happiness is also important and the future happiness is also important. So there is a weight over what happiness matters to you. The current RT plus 1 is the reward you get. In the future, happiness is discounted by something called discount factor, which is a value less than 1. If the discount factor value is greater than 1, what will happen? You are giving too much value to your future happiness than your current happiness. Alright? So now let's go with the mathematics. After defining this, I took a gamma common in the third mathematical equation. Now this internal term is nothing but the future expected reward from time instant T plus 2. That is what I substituted that GT plus 1. Now that is now GT plus 1 expectation is nothing but value of the state ST plus 1, the next state. Is the equation clear? Anybody has any doubts here? You can just raise your hand. It's all right. Okay, so moving forward, just remember this. This is pretty important in the future slides. Values of the value function. Please stop me if you do not understand this. So now the value function. There is some. This guy got a big brother called Q value function. This is the expected reward you get from the state S upon doing an action. It's defined almost the same, but you also have an action term here. Alright? See, the definition and the equation is pretty similar. Q pi S of A is expectation of the rewards you get in the future and the expected reward from the next state. Let's go to the first model-based reinforcement learning algorithm. Now we established some technicalities and terminology. We will be diving into the first algorithm. It's a model-based reinforcement learning algorithm. What does model-based reinforcement learning algorithm mean? Anyone? Right, it has the transition probabilities. So model-based reinforcement learning. Everything in model-based, Bellman is a guy. What's Bellman equation? As I already said, you need to store your information in a compact manner. How do I store it? I describe something called value function, which gives me the expected reward. This is what the information I'm storing. You saw this equation. How do you remove this expectation variable? Do you know how to? Anybody knows probability statistics here? Anyone? Anyone know how to remove the expectation? For question 2 NR 221, one guy can answer. Raise your hand. You can get your goodie here. Anyone? Expectation removal. Anyone from NR 122 or 2222? Sorry, not 1. This is to be fair with both the rooms. Just bear with it. No one? Alright, no one answered. So moving ahead. See the scary graph, scary equation. Don't worry, I'll give a step-by-step explanation. What was this? Here, the expectation, the definition of expectation is there is a random variable inside the expectation. You multiply with the probability of the random variable taking some value. And you do a sigma over all the possible values the random variable takes. Now, what defines a model is the action and the state. So here my random variables are actions and states. Now in a state S, you can do any one of the action from the action space. So pi AS, as I mentioned, is a probability of taking an action. That multiplied by internal term. Now in the internal term, from doing an action, you can reach to many of the states. A single action, you might be lucky and be a billionaire, or you might end up tragic. There is a probability of going to any of the states. So there is a sigma over the states, next possible states. So this is a definition of expectation. You have to trust me on this. And remember this. This would be pretty much clear if you guys have probability basics. Okay. So similar equation to the Q value, where the action is already given in your function. So you have the reward plus it goes inside your equation, all right? Equation is useful anyways. In this equation, you know two things. Upon a state and an action, you know the reward. RAS is known here. And probability because it's a model-based learning algorithm. Things you do not know here is the policy and your value function. This is what you have to learn here, right? So if you learn your policy, you're done with the problem. You know what action to take at a given state. Assume now that you know the value of the states, how do you find the best policy? Knowing values, you know the expected reward you get if you are present in a state. If you know this, how do you predict the optimal policy? It is simply a greedy policy. You are standing in a state S, you will choose the action, whichever action gives you the highest expected reward, that is your action at that state. Right? So this is what is shown. You find the action which gives the maximum of expected reward and assign a probability of 1 to that action. And all other actions will have a probability 0. Is the equation clear? It's a maximum of A over this. You substitute all possible A's and you get the maximum value of B and you got the optimal policy. Remember, I asked you to assume you know the value function, but how are you going to know the value function? If you are in the state, how do you know how much reward you're going to get? Let's find out. Can anybody see the problem here of learning the value function without learning the policy or vice versa? Can anybody find the problem here? Can you learn the value without learning the policy, or can you learn the policy without learning the value function? If not, why? Anyone? Loud, loud. All right. So the problem was in the Bellman equation, as you saw, the Bellman equation estimates the value function, right? In that Bellman equation, you found a policy term inside the equation. If you are going to learn the value function, you need to know the policy. But your policy is a greedy policy. The policy uses the learned value function and predicts the action. Then this is a coupled equation. How do you solve without solving one of this? So we go with iterative methods to solve such coupled problems. Let's start with the random policy. Initialize all the probabilities randomly and all the values randomly. Now there is a step called policy evaluation. I'm going to go into the details in the next slide. And there is a step called policy improvement. You do this in the loop, you will end up learning the value and also the policy together. You see the diagram here, right? So first is the policy evaluation. It will evaluate the policy. Then the first arrow. The downwards arrow shows you will learn the policy with an estimated value function. And you do this for a sufficient number of iterations, you will end up with the optimal value and optimal policy. So there is the iterative policy evaluation. This equation you guys already saw. This is the Bellman's equation of estimating the value. In this equation, make note that this is bk plus 1 and this is bk inside the equation. Here k is the iteration number. So in the kth iteration, you estimated the value of a state and you equate it to the k plus 1 iteration. Similarly, you update your policy using the learned value function. This need not be an optimal policy, but you will end up with the optimal policy after sufficient number of iterations. I'm not going to prove this convergence, but you can look it up in Richard Sutton's book. Okay, note down this. Richard Sutton is the father of AI and reinforcement learning. This is the same thing I just explained. You do the value estimate, then the greedy, you do it in a loop, you end up with the optimal policy and value. Right. You learned your first reinforcement learning algorithm. You successfully estimated a value function, successfully estimated a policy. Now you can do actions given a state. By the way, this method is called value iteration. Okay. Here is a demo of the algorithm you just learned in play. This is a knight and princess problem. My friend here is going to demonstrate this.
Okay, guys, I'm Rahul, earlier computer science undergrad as well. So you all should have read the rules of this game, right? So you are the knight and you need to save this princess, and for that you need to step that into the castle of the map. However, it's not for free. At every step you lose 4 points. And there are the plus point is that the enemies are fixed; they cannot move out of the tile. If you touch the enemy, you lose 100 points. However, if you just reach the castle, you can gain 100 points. So how do I create an agent for this? Any idea? Okay, let's simplify the problem. I'll first color all these styles. Let's say it's a 5 cross 5 map. So for the position of the enemy, I've just marked it red, and for the castle, it's green, and agent is currently marked by yellow. So talking about the state space and action space, how many states are here? How many possible states? Sorry? How many possible states, like this agent can move anywhere, right? However, the enemies are fixed. So 25 states, right?
Since it's a crowd answer, nobody is getting the footage.
Okay, so 25 states, and the agent can move anywhere up, down, left, or right. So there are 4 possible axes. So if you just make a matrix, it will be 5 cross 5 state space, and you have this 4 action space. So maybe I can just learn this using a. So some of you must be familiar with dynamic programming, right? How many of you are familiar with dynamic programming? So this approach is very similar to dynamic programming. I will just create a table of 5 cross 5 cross 4, and we'll simply do the same value iteration thing to learn this algorithm. Okay, so let's see how it performs. So basically, this agent is just exploring the entire state space, and wherever it's finding a reward, it is just updating the table, and eventually it will find the optimal policy that is the shortest path. So you can see it has already found it. So it hardly took 30 to 40 seconds, right? Or not even that. However, as you increase this dimension of the matrix, let's say I make it 10 cross 10, then it will be really difficult or time consuming. Everyone is clear with this, right? Like I've just used this matrix and updating the values.
Don't worry, he'll be back with one more demonstration. So you all understood how this works, right? How is the policy iteration algorithm, the value iteration algorithm I just discussed is working. At every state, it is finding an action and performing it and calculating the reward and updating its value function. Here the value function is Q value function, or don't worry about it, just think of it as a value function. And then it is also updating its policy. And this is doing it in a loop. After certain steps, the policy converged and it found the optimal action as you saw. Seems good. We could do this only because we know the transition probabilities. And you go to the upward block upon pressing the up arrow. But this is to be known by the agent. If it does not know it goes to the upward block by pressing up arrow, it cannot do anything. Not quite true. It can do something, it can learn this. Estimating Q value without state transition function. Also known as model tree learning. I hope you remember this equation in this diagram. I just showed it. You evaluate your policy. That means you update your value functions and then you update your policy. This happens in a loop. Now, in the policy evaluation step, previously we used the Bellman's equation. In the Bellman's equation, there is a transition probability term. Now we do no longer know the value of transition probabilities. So how are we going to estimate the value function now without the Bell-Wells equation? This algorithm is called Monte Carlo algorithm. Without the Bell-Wells equation, there is another numerical way of getting the estimates. How many of you know how to take an average? If you do the same thing for, let's say, million times, and you take the average of this, you know the estimate, right? That is how this algorithm works, Monte Carlo. You don't know the transition probabilities, so you run the system for a million times, million number of examples, and you estimate it. Here, n of st, at is the number of times you arrived at the state and this action. This is the running average equation of finding the Q value function. How did we arrive at this equation? I'm going to show it in the next slide. So now Q of st, at is your value function at some instant. Let's say after running it for n minus 1 steps. Now if you want, you again visited the state st, at. Now you want to update the Q value. How are you going to do it? You multiply the current Q value with n minus 1, add the reward you found, and divide by n. This is simple average equation. I hear noise in the crowd. Is it clear? Everyone? It's a simple average. You just add the reward and divide by the total number of terms. Now if you rearrange the terms here, you arrive at the Q of st, at equation shown here. So if you run this for sufficient number of times, you will be able to estimate your Q value. Now taking the average over here, each term is a GT term. GT is our expected future reward. So for this, you have to complete your episode. So as I said, your situation is a sequence of steps. Once your number of steps is terminated, you reach the conclusion point. Only then you can get your reward. Because Q is our expected future reward. The future is defined only when there is a termination. Else it's an infinite future, right? So once the future is determined, at the end of the episode, you get GT. So in order to find the Q value, you have to wait till the completion of the episode. What happens if the episode loops? It takes infinite time to stop. This is trouble, right? You cannot estimate your Q value. So some other guy came with temporal difference learning. You need not wait till the end of the episode to estimate the Q value. You estimate it on the go. This equation is exactly same as the previous equation, just that in the GT is the final reward you get after the termination of the episode. Now I am replacing GT as the reward you get at the current situation plus expected future reward from the next state. Right. So you have estimated your Q value. Now you can get the optimal policy from the estimated Q value. And you are done. You have your first model-free reinforcement learning algorithm. Now I'm just going to give some insights about some advanced algorithms. This is something called Q learning algorithm, where your policy, everybody remembers what policy is, right? The policy which you use to generate the examples or the episodes is different from the policy which you learn. If such an arrangement is made, it's called an off-policy learning algorithm. This is beyond the bootcamp, so I guess I'm not going to go into the details of it. Okay, this is a goodie question. Did you notice something very important about states and actions till now? Something very important regarding the states and actions. How did we do, or how did we perform each of our estimate? Anyone? Anyone from NR 222? All right, I'm going to reveal the answer. They are finite. The number of states and the number of actions, they are finite. You cannot deal with an infinite state space and infinite action space because you are taking a sigma over the states. If number of states are infinite, how long are you going to take the sigma? How do you compute the expectation? Then all the points, data 2, the images, it's a real number. It's an infinite state space. And your action, you can move in any direction with 360 degrees with different velocities. This is all real